This tutorial, Solution Stiochiometry 2, involves stoichiometry problems that use net ionic equations. Remember, a net ionic equation involves ionic compounds that have dissociated, and in the process we have removed the spectator ions, or the ions that aren't involved, and are just looking at the ions that actually are creating the products. Now, before we do a stoichiometry problem, I just want to remind us about how the formula of compounds can be used to determine the relationship between the different parts of the compound. For example, in this question that I've written down, it says you have a solution of sodium phosphate, and the phosphate ion concentration was determined to be 0.250 molar. What is the sodium ion concentration? So in this case, we're looking at two parts of the ionic compound sodium phosphate. We're given the phosphate ion concentration and asked to find the sodium ion concentration in the same compound. So we're going to start with the concentration. We have 0.250. Now it's molar, which means it's moles of phosphate, because that's what they told us this was, per liter of solution. Now the question is asking us about the sodium ion concentration. Well, if I look at the formula, I see that there are 3 sodiums for every 1 of the phosphate. Remember, in polyatomic ions, if there's more than 1, we use parentheses. So I can use, that could be used as a mole ratio. I would put 3 moles of sodium on the top because that's what I'm looking for, sodium ions, and I'm getting the 3 because there's 3 of them in the formula, over the ratio of 1 mole of phosphate. So again, what happens, it's all about conversions and using our units. The moles of phosphate cancel. And so now if I multiply it, so I would say 0.250 times 3 divided by 1. So I would get 0.750 moles of sodium, sorry that's kind of crowded, per liter. And in terms of molarity, remember molarity is moles per liter. So the concentration of the sodium ions in this very same solution is 0.75 molar. Now this is not a stoichiometry problem in the sense that it doesn't involve a reaction, but it's just a reminder about how we can use the ratio of ions in a compound formula to help us convert to different parts of the compound. So let's take a look at a stoichiometry problem. So this problem says how many milliliters of 0.5 molar KOH are needed to react completely with 60 milliliters of 0.250 iron 2 chloride solution to precipitate the iron 2 hydroxide. Then they give us a net ionic equation. So basically we're interested in knowing if we have 60 milliliters of iron chloride, how many milliliters of the potassium hydroxide will we need? Now we can use the net ionic equation to figure out a ratio between these two compounds. I can see here that in front of the iron isn't anything, so I know that's a 1. And then there's a 2 here. So it's a 2, let me write it darker. So it's a 2-to-1 ratio. But before I use that ratio, I have to convert to moles. So when you have solution concentration, you can take the volume in liters. So I'm converting the 60 milliliters into liters. And you multiply it by the concentration. Now, in these kind of problems, it's helpful to remember that concentration means moles per liter. So I'm going to rewrite this as 0.250 moles of iron chloride in every liter of the solution. Now liters cancel. And if you'd like to get an answer right now, you can. I like to do this as a continuous problem. but I like to think about it as I go, and right now I have moles of iron 2 chloride. Well, my equation up above was a net ionic equation, and it gives me the ions. So I can change this into the ion concentration because I know, looking at the formula now for iron chloride, I'm looking at this formula here, I know that in that formula there's 1 mole of iron, because there's only one of them, in every mole of the iron chloride. And so now I can cancel out the iron chloride. As you can see, as I'm just converting step by step using ratios. If I stop right at this moment, I have moles of iron 2 plus. Look, I've canceled out liters, and I've canceled out moles of iron 2 chloride, and now I have moles of iron 2. So if you're going by step and you wrote an answer here, your units would be moles of iron 2. Now I'm working my way, because remember the question wants to know moles of potassium hydroxide. Well, now I can use the net ionic equation to connect the moles of iron to moles of hydroxide. I'm getting closer. So here now I could say, all right, I see from the equation that there's 2 moles of hydroxide ion, and I'm looking right here. This is where I'm looking to get that. For every 1 mole of iron 2 plus. And I'm looking right here at the coefficient. Okay, so this equation right here, this ratio this ratio right here is the ratio from the balanced equation. That cancels out moles of iron 2 plus. Now this whiteboard that I have on my iPad won't let me keep going, but I'm going to keep going, but it won't let me be continuous, like I can't keep going straight. So I'm going to have to come down here. So now, looking at the units from the very beginning, this is going to take a little highlighter. I canceled out liters, then I had moles of iron chloride. I canceled out iron chloride using the ratio from the formula. I canceled out iron using the ratio from the balanced chemical equation, the net ionic equation. Now I'm finally, right now I have moles of hydroxide. I am so close. I know from the formula up here that hydroxide to potassium hydroxide is 1 to 1. Now mathematically, you know this is not going to change our answer, but I like, whoops, oh sorry, I did something that made it open up. I like to cancel all my units. So cancel and cancel. So now I have moles of potassium hydroxide. Okay, if you have moles of a substance and you know the concentration, you can calculate the volume. So I take the moles of potassium hydroxide and I'm going to divide it by the concentration, because I know from my problem, looking up here, that I have 0.500 moles of potassium hydroxide in every liter. So I'll cancel out the moles of potassium hydroxide. Now when I get my answer, I'm going to have liters of potassium hydroxide. So let's get that. So I'm doing in my calculator. 0.06 is the first step, times 0.250. Then the first ratio is 1 to 1, so it's not going to change my answer. I'm going to the next ratio, which is 2 moles hydroxide to 1 mole of iron, so I multiply by 2. Then the next ratio is also 1 to 1, so it won't change my math answer. And then the last ratio I'm going to divide by the concentration, which is 0.5. And I get 0.0600 liters. Okay, now then to convert this to milliliters, I'll multiply by 1,000 or move the decimal over, and I get 60 milliliters of KOH. So you can see from this problem that what we answered is if we had 60 milliliters of 0.25 molar iron chloride and we wanted to react it with 0.5 molar potassium hydroxide, it would require 60 milliliters as well. You can see with the ratio, some of it was 1 to 1, so you may think, oh, I could do this more simply, and you could. But if you follow through the ratios, canceling the units, you're sure not to miss any steps.